Okay, so we'll start with Newton's law of cooling. We'll do two examples of that, and then we'll look at logistic growth. We'll do just one example of that. And if you look at Newton's law of cooling, you get this nasty looking formula. Again, I'm not going to ask you to memorize this formula. I personally don't have it memorized either. As you take calculus, you learn how to create this formula from scratch, and it's actually a very simple calculus procedure, which is why I don't have it memorized, because I'd rather just create the formula when I need it, as opposed to memorizing it. So T of T, that's capital T for temperature, little t for time, is equal to the quantity of T0, the initial temperature, minus T sub S, which would be the surrounding temperature, times e to the kt, well, e is a constant. K is the number we will be looking for in these problems, and then of course that little t is time again, plus T sub S, the temperature of the surrounding medium. So our whole goal here is going to be about finding K. And finding K in every one of these problems is going to come back to the same thing that you talked about on Friday, and that is the two data points method. So it's really about substituting a bunch of values in and doing a little bit of algebra to find the K value. Now, in the problems you did Friday, that K represented the continuous growth rate. That's not the case here. K is just some random number known as the constant of proportionality, and it's just going to be our job to find that value. So let's take a look at a couple of examples. You know what, before I do that, let's talk about what Newton's law really says, because in terms of that formula, it doesn't mean anything to most people. Your hand is 98 degrees. Put it in some water that's 80 degrees. What's going to happen to your hand? It's going to cool down. It's going to cool down towards 80 degrees, right? How fast will that happen? No. What if you put it in water that was 1 degree? Would it cool down more quickly or less quickly than if you put it in water at 80 degrees? More quickly. How come? The bigger temperature difference. What happens if you put your hand on the burner on the stove that's 400 degrees? Your hand almost instantly goes to 400 degrees, doesn't it? Why does that happen so quickly? What Newton's law says is, the further apart the two temperatures are, the more quickly they will come together. So the fact that the burner is 300 degrees hotter than your hand means your hand is going to rapidly approach 400 degrees. If you put your hand on a burner that's 110 degrees, your hand will warm up. It'll take some time. So what the rule says is, the further apart the temperatures are, the faster they will come together. Your hand is going to get to 400 degrees almost instantly when you put it on a hot burner. Okay, so we take a 98 degree hard-boiled egg and we put it in a pan of water that's 18 degrees. What's going to happen to the temperature of the egg? It's going to get colder, and if I leave it under the water long enough, what will it go to? It'll go to 18 degrees if I leave it under that thing long enough. Now that's all theoretical, because technically the egg is going to warm up the water a little bit too, and they'll meet close to 18 degrees, but that probably won't actually get 18 degrees. Okay, so we're going to take the data here and we're going to come up with the value of K, and with that value of K we should be able to answer a couple of questions. Okay, so I need to fill in a table by hunting through the text. What are we going to use for T sub S, the temperature of the surrounding medium? That's 18 degrees. I'm going to put it in a pan of water that's 18 degrees. At time 0, what temperature do I have? 98 degrees. And then 5 minutes later, the temperature has dropped to 38 degrees. All right, well, this is going to be easy enough to fill in. The temperature at any given time is going to be calculated by T0 minus Ts. So I want to say that's 98 minus 18 times e to the kt plus the temperature of the surrounding medium. Another 18 goes here. So this 98 minus 18, let me simplify that. We're going to call that 80. And T as a function of T, the temperature is dependent on time. I'm just going to call that capital T for that. I need K. If I look at this thing, how many variables are in this equation? Capital T, little t, and k. So if I want to solve for k, I need to get rid of two variables. How can I accomplish that? How can I get rid of the capital T and the little t here? Which numbers? Yeah, plug in that second data point. So we're going to go with 38 degrees has to equal 80 times e to the 5k plus 18. I'm fairly confident you can solve this. How would you do it? Subtract 18. If I subtract 18, this becomes 20. And it goes away. What next, Alex? Divide by 80. This becomes 0.25. And that goes away. Now what, Ryan?
Natural log.
Take the natural log here. And what is the natural log of e to the 5k? So k turns out to be the natural log of 0.25 all divided by 5. All right, now I'm going to go to my calculator and I'm going to put that value in. I'm going to take a look at the function we've created. So natural log of 0.25 my k value here is negative 0.2772588,722. I'm going to store that as k, and then I'm going to enter this function into my calculator. So we came up with the function 80 e, k, x is now going to be time, and then plus 18. Well, if I've done this correctly, the graph that's created should contain the points 098 and 530. So let's take a look at a window. Let's go, we got an egg sitting in the water. Let's say we leave it in there for 60 minutes, and the temperature we started with was around 100. So we'll just go y max 100. And here's a picture of the curve, decreasing exponential. Let's check to make sure I'm on the right track. At time 0, the temperature is 98. 5 minutes later, the temperature is 30. So we've nailed it. K we came up with was the natural log of 0.25 divided by 5. When will the temperature reach 20 degrees? Sam, how do I determine when the temperature reaches 20 degrees? Here's the equation we're working with.
Is the big T the temperature?
Yep.
Then we'll split the 20 for T.
Put a 20 in for T. That's all. Subtract the 18, divide by 80, take the natural log, you've got it all done. If you're going to do it on a calculator, nothing more to do here than graph y equals 20, find the intersection. 13.304 minutes later, you'll have your egg down to 20 degrees. Now my curve has a horizontal asymptote. What is the value of that horizontal asymptote? 18. Because what's happening? The temperature is heading for room temperature, and then it's going to sit there. I guess it's not room temperature here, it's the temperature of the water it's sitting in. Okay, so that's how you deal with Newton's law of cooling. Just like Friday's work, it all comes back to, can you find the constant of proportionality? And in order to set it up, you have to do the reading, and you have to set up your own table with a couple of data points. So, take a look at this second problem. Tell me what to write down to get things started. 070. I don't think so. 180. Cup of coffee is initially 180 degrees. 100. And the surrounding medium temperature is 70. So the temperature at any given time is going to be T0 minus Ts, correct? E to the KT plus Ts. Therefore, temperature at any given time is 180 minus 70, which gives me 110, E to the KT plus 70 on the end. What am I going to have to find? I'm looking for K. How do I get it? Substitute what? 10 and 100. Let's use this second point to find the K value. So 100 is 110 E to the 10K plus 70. Anybody want to tell me the value of K without writing anything down? Do the mental gymnastics right now. See if you can tell me it. Close. Say it again. You what?
I already wrote it down.
How'd you get it? Did you? Oh wow, you just buzzed through it. What's got to happen? I've got to subtract 70. That's going to make this 30. I've got to divide by 110. And then I'm going to take a natural log, and I'll end up with the natural log of 3 over 11 is equal to the natural log of e to the 10k, which just happens to be 10k. And k turns out to be the natural log of 3/11, all divided by 10. So it's kind of similar to finding k from Friday. If you look at a couple of things, number one, the denominator is the length of time that took place. And the numerator is always the natural log of some quantity. Let's check to make sure we're on the right track. Done it. You go back here. Natural log of 3/11, all divided by 10. I'm going to store that as k, and I'm just going to use the letter k. Plus 70. Okay, again, a window, we're talking about a cup of coffee. I don't know, that thing might sit around for a couple hours, so we'll go 120 minutes. The initial temperature is 180, so let's go up to 200. Here comes the coffee on its way down. Again, I want to check this, so let's check to make sure the points in our table are on the curve. 0, 180 is there. 10 minutes later, it's supposed to be at 100. What are the y coordinates on this line going to be close to? 7. You let the cup sit there, and it's going to approach room temperature, and then it's going to stay there. Okay, so after how much time does the coffee reach a temperature of 90 degrees? Simply intersect it with the curve y equals 90. And you got it. 13.12 minutes later, we're at 90 degrees. So that's not terribly hard. The formula is ugly, but you don't have to get too deep into it. And again, I'll mention this. In calculus, we derive that formula. And it's not a hard time. It's not a hard topic at all. It's one of the easier things they do in calculus. All right, so we're halfway home. Now we need to look at a different topic, and that topic is logistic growth. And again, what you're going to see here is a really nasty formula that you don't have to memorize. And we don't derive this one in calculus. I was showing somebody this morning that to derive Newton's law of cooling takes 5 steps in a calculus class. And then I showed him the derivation of this formula, and it was 35 steps long. So that isn't something you're going to have to worry about. The most important thing you have to know about logistic growth is what it really means. So if we go back to the dog problem, let's go back to that dog problem from Friday. That dog had an initial weight of 2 pounds, and what did it grow to? 3.5 pounds? 3.5 over 2. And that took 2 months to happen, didn't it? So to the t over 2 pounds. That's actually the formula for the dog's weight. And the question said, how much does it weigh after 6 months? That's a different version of than how you did it, but it's the same formula. So we've got 2 times 3.5 divided by 2 raised to the t over 2. And if we look at this dog's weight, you'll see that the dog grew. At time 0, he was 2 pounds. 2 months later, he was 3.5 pounds. After 6 months, he's 10.7 pounds. After 3 months, he was 4.63 pounds. That's what the question asked. But the thing is, if you let this dog grow long enough, let this dog grow for 10 years, well, he's out of control. After, yes, it sort of happened to Clifford, but not really, because the Clifford didn't get anywhere near. So let's see what happened to this dog at the end of 6 years, so 72 months. Yeah, he weighed 1 billion pounds.
It's not as big as Clifford.
So what happens is, the rule we studied, P of t is P0 e to the kt. Remember what they called that? The rule of uninhibited growth? Well, yeah, there's no such thing as uninhibited growth. You can't just grow forever. There has to be some limiting quantity. You know, there are deer running all over South Dakota. And if you let them grow forever, they'll grow forever. But at some point, it's just going to stop. The population's just going to stop increasing. How come? They die. Why do they die?
Not enough food.
Not enough food. They'll starve, and then your curve will flatten out, and the population will stop growing. That's why they say, you know, the population of the Earth of the people on Earth is going to be a problem, because people grow exponentially, whereas the amount of food produced by farmers is growing linear. And so the exponential will outgrow it, and it'll be a food problem at some point in time. Anyway, the dog's weight can't grow unchecked. So what they say about the law of uninhibited growth is it's only good for short periods of time. It doesn't predict long term. More likely what's going to happen is this dog is going to grow quickly at first, and then his weight's going to level off, and he's going to go like that. Okay? Let me give you another example. Suppose I give you a job, and I say, I'm going to pay you 1 penny to do this job today. Will you take the job? I'll pay you 2 cents tomorrow. I'll pay you 4 cents the next day. 8 cents the next day. You're not going to take this job? I'm going to double your pay every day.
Eventually, but the 8 cents is not really enticing.
Yeah, but I'm going to double your pay every day. You'll take it? I'm going to show you a number. I'll show you a cool number. Take a look at this number. 24 hours in a day, 3,600 seconds in an hour, 365 days a year, and the age of the Earth is 5 billion years. So that's the number of seconds that has gone on since the beginning of time. Now, if I double your pay every day, and you keep this job for 2 months, here's how many pennies I have to give you on the last day. I'd be giving you more pennies than there have been seconds since the beginning of time. And that's just for 1 day's work. What about the day before? Well, then I only had to pay you this much. Still, that number is bigger than this number. 4 times bigger. So, exponential growth cannot go on unchecked because the numbers just become ridiculous. So, there's always a correcting factor. And the logistic curve takes correction into account when it applies. If you look at this, it looks like it's taking off exponentially, but then it changes its mind and slows down. That's what it really is. And again, this is an incredibly hard formula to create, but it's very easy to work with. A, B, and C are going to be constants. The model is a growth model if B is bigger than 0. It's a decay model if B is less than 0. You don't have to know that. There's what they always look like. If an increasing logistic, it'll do this. Decreasing, coming down. The number y equals c is known as the carrying capacity. It's the biggest value this curve can reach. It's also the numerator of the logistic curve. Halfway up, you're going to get what's known as an inflection point. And it goes like this. You're concave up like a cup, and then the curve goes to concave down like a frown. Concave down like a frown, then we go to concave up like a cup. Essentially what it means is that the rate at which you're increasing is going to start to slow down. Very steep curve starts to flatten out. So here are the things you need to know. The domain is the set of all real numbers. How come? No square roots, no logarithms. What else do we have to worry about? I can't make the denominator 0 because it's 1 plus something that's exponential. That's always positive. It doesn't have any roots. If you want to find the y-intercept, you simply plug 0 in here. There are 2 horizontal asymptotes. One will be at 0, the other one will be at this number, c. It'll be increasing if b is greater than 0, decreasing if b is less than 0. Inflection point will be halfway to the carrying capacity, and that's about it. And the carrying capacity is this number. That's the most important question. So here's an example. We got fruit flies. We're going to put them in a half-pint bottle of milk with some food, and we're going to have them modeled by this equation. 230 over 1 plus 56.5 e to the negative 0.317. Divided by the quantity. Okay, so t here is being measured in days. Let's see what happens after 30 days. And y is the population of fruit flies. How big do I need this number to get? 230. Carrying capacity in this case is 230, so I don't have to go any higher than that. So here they are growing rapidly. Oh my word. My kitchen, my country, my world is going to be overrun by this population of fruit flies. However, thankfully, it's decided to correct itself and slow down. Because there's just not enough banana in there to feed a population of billions of fruit flies. So, you see the horizontal asymptote at 0, you see another one at 230, and no matter what I do here, maybe I'll let these things grow for 90 days. Lo and behold, oh, thankfully it flattened out. State the carrying capacity, 230. This milk bottle is not capable of supporting more than 230 fruit flies. Determine the initial population. P of 0 is 230 over 1 plus 56.5 times e to the 0 power, well that's 1, 230 over 57 and a half just so happens to be 4. There were 4 fruit flies present when we started this experiment. Find the population after 5 days. Tell me what to do here. Taylor, what do I do?
Plug in 5 for T.
Plug in 5 for T. And that population is 23.27, and that's all there is, really. The other question that could be asked is, how long will it take for the population to reach 100? In which case I would simply put 100 on this side and solve that. So, not a great deal of difficulty. Again, you've got 2 not very user-friendly looking formulas, but you don't have to memorize them. I'll always give them to you. You have to be able to use them. Oh, one question I should have asked. What's the growth rate? 37%. It won't be a negative number. If you look at the formula has the negative right there in it. So the growth rate here is this number, and it's just 37%.
So why is it negative?
That's how the formula is derived. There's a negative next to the growth rate. That's what I've got to say about it. I want you to try just 5 problems here. There they are, page 337 to 339, problems 13, 16, 24, 25, and 27. That's all you need.
That